Okay, question 7. A student investigates the reaction between sodium hydroxide solution and hydrochloric acid. He uses this method. Step 1, he added 50 cm cubed of dilute hydrochloric acid to a conical flask. Let's draw that out so that you can really see it. So this is a conical flask. It's the ones that have a sort of have a neck, right? And then the hydrochloric acid inside is going to be HCl. And since it's dilute, that means you've added water to it, and that's why the state symbol is aqueous. All right, then what did he do? Then he added a 5 cm cube portion of sodium hydroxide solution into the conical flask, and then he tests the pH of the mixture using both universal indicator paper and a pH meter. And then he keeps repeating it until a total of 50 cm cubed of sodium hydroxide solution is added into the conical flask. So question A1, state the piece of apparatus that should be used to measure 50 cm cubed of hydrochloric acid. So some of you guys might write beaker or even test tube. These two are wrong. Test tubes do not have any markings on it. Next time you're in the lab, look at the test tube. It doesn't have any measurement markings on it, so you can't use that to measure anything. Beakers also are not accurate enough. So the accurate ways to measure a volume would be a measuring cylinder, or you can put a burette, because you use that a lot in titrations, right? And those are very accurate, or even a pipette. So these two measuring instruments used in titrations are very accurate ways of measuring volumes of liquid. Part 2, name the type of reaction that occurs between hydrochloric acid and sodium hydroxide. So I hope you can recognize that this is an acid and that this is an alkali. And in case you're not sure, make sure you know the following 3 acids: hydrochloric acid, sulfuric acid, and nitric acid. These 3 acids, because they're the ones that appear a lot in past papers and also ones that you actually use in the laboratory. Alkalis, there's 2 types. There's metal hydroxide. Any metal hydroxide. Hydroxide is just OH minus, right? So it's any metal that's combined with this OH minus. In this case, it's sodium that's combined. And then another one not everyone knows is that metal oxides are also alkali. So that means whenever this group reacts with this group, you will have, think about it, acid and alkali. What do they do to each other? They will neutralize each other. So therefore, this is a neutralization reaction, okay? And neutralization reactions always produce the same products, which is water and salt. So just to make sure you really understand what's going on here, let's write out the actual equation, shall we? So this is HCl, which is the acid, and the base is sodium hydroxide. Add sodium hydroxide. And what are the products? Now, if you're ever stuck thinking what are the products of a chemical reaction, just look. The blue ones I've highlighted are the positive ions, right? And then the green ones I've highlighted here, these are negative ions, also known as anions. And if you're not sure what happens in a reaction, a lot of the times they just switch partners. So that's like your best bet if you have no idea what are the products. You just switch the partners. So look at this blue hydrogen here. It's bonded with the green chloride, right? Now, if it was to switch partners, it's going to bind with either this blue one or this green one. Who would it bind to? Have a think. Which one will the hydrogen ion on the left bind with? Will it bind with the positive sodium or the negative hydroxide? Opposite charges attract, right? So therefore, this positive one will bind with the negative hydroxide, and also this positive sodium will bind with the negative chloride, and therefore my products will become, for this one, that's H2O, literally water, H2O, plus, when these two combine, NaCl. Make sure you write NaCl, not ClNa, because it's the positive ion that's always written first. Okay, and neutralization always produces water because water is neutral, has a pH of 7, and a salt. Salt is just a ionic compound, in this case, sodium chloride. Okay, then it says, graph 1 shows how the pH of the mixture changes as the sodium hydroxide solution is added. Right, so over here we have volume of sodium hydroxide solution added, and then we have the pH. Now, do you understand what's going on here? Think. You have do you remember we had the HCl in here, right? Which is an acid. And then you're gonna add sodium hydroxide, which is this one down here. So think about it. At the beginning, when you haven't added anything, what will be the pH of this acid? What is the pH of acids? I've got it here for you. pH of acids will be anything that is less than 7, right? And if it's a very strong acid, it will be even lower. So the lower the pH, the more acidic. And conversely, the higher the pH, the more alkaline it is. So I hope you remember this pH scale, right? This pH scale. So therefore, when we come back to this question, at the beginning, when you haven't added any sodium hydroxide, it's just the acid in the conical flask. So you would expect that the pH would be very low, especially that HCl is a strong acid. That's why it's 1. It's got a pH of 1 at the beginning. And then as you add more sodium hydroxide, which is an alkali, you would expect that the pH will start to rise, isn't it? Because that's what alkalis have. They have higher pH. So that's why it goes up. So I hope you understand why this graph is sort of like an upward trend. All right, then it says, determine the pH after 40 cm cubed of sodium hydroxide solution has been added. So this is simply graph reading. So at 40, let's make this very accurate, very, very accurate. So at 40 cm cubed, what is that number over there? That would be 12.4. Agree? 12.4. You have to be very accurate. Not 12.5, not 12.2, 12.4. is the pH. So be very accurate when it comes to graphs. And then part 2 says, suggest the color of the universal indicator paper when these volumes of sodium hydroxide solution have been added. So it's asking for the color. Read the question carefully. It's not asking for the pH. So it's not like, oh, 15, I'm going to go 15 and 2. No. It's not asking for the pH. It's asking for the color. And I hope, again, back to this picture, isn't it? So therefore, remember, if it's acidic, it'll be this red for strong acid and a yellowish for weak acids. And then purple for strong alkali, and then greenish blue for a weak alkali. So knowing that, let's have a look. When it's 15 cm cubed, that will be over here. Over here, so 2, pH of 2. That's pretty low, pretty strong. So I would put down like orange, red or orange, isn't it? It's not high enough to be yellow, so it's red or orange. And then what about 30 cm cubed? 30 cm cubed, let's look at that. Wow, all the way up here, 11. So remember the green bit was 7. And then colors of the rainbow, after green, it becomes blue, and then all the way up to purple. So 11 would definitely be in the bluish range, right? Blue. 11. You can see here. See? 11, blue. And I've also, just for your revision purposes, I've put all the indicators that you have to know at IGCSE, including their colors and acid and base here for you, just so that you can have it all in one place to help you revise more comprehensively. And I've also shown you, actually over here, this is an example of phenolphthalein where, do you see, guys? You see how originally it was colorless, which tells you that this liquid originally, since it's colorless, it was an acid. And what color does it turn when it becomes pink? It's when it's in a base, right? Or the solution has turned into a base or an alkali. And that's the moment, you see what it's dripping, the moment it drips down here, that the solution has become neutralized, and therefore next one would be alkali, right? That's when it turns pink. So very striking. And if you've done this experiment in school, you'll see that it's a very sharp pink color. Okay, great. Part C. Now it says, another student investigates how the temperature changes when the sodium hydroxide solution is added to the hydrochloric acid. So he's looking at temperature change now. And the hydrochloric acid and the sodium hydroxide solution are at the same temperature at the start of the investigation. Then the student records the temperature of the mixture after adding each 5 cm cube portion of sodium hydroxide solution. So 5, record the temperature. 5, record the temperature. Another 5, record the temperature. And the graph shows her results. And then it says explain the shape of the graph. Okay, so in these past papers or the exam paper that you're going to take, there will always be some sort of graph interpretation, and it'll ask you to describe the graph, explain the graph, and just look, it's 3 marks. You have to be very systematic with how you're going to answer this question. Just look at the graph, right? What are the 3 things you're going to talk about this graph? What's like the 3 most striking things about this graph? 3 most striking things. The first one I would say is obviously this turning point. So I would be talking about that. Let's say that's part B of the graph. Then the other point about this graph is this whole area, which is going up, right? So let's call that part A of the graph, and then obviously going down, part C of the graph. So if you just look at the main parts of the graph, now you can explain it based on that. Now you cannot just say, oh, it goes up and then it goes down. You won't get any marks for that. Do you know why? Because this question tells you to explain the graph. It means that you have to give a reason for it going up. So you really have to think why it's going up. The reason it's going up, well, think about it. What kind of reactions make the temperature go up? So the first point is exothermic reaction, right? Exothermic. Exo means exit, thermic means thermal. So the exit of thermal energy, the exit of heat comes out, and that's why the temperature goes up. So exothermic reaction. Therefore, the temperature goes up. That's part A of the graph. Temperature goes up. And then at B, any turning point on a graph, I would put down that number because it shows that you're reading the graph carefully. So B is the highest point, which is 25 cm cubed of sodium hydroxide solution added. So I would say here, when 25 cm cubed of NaOH or sodium hydroxide over here is added, what is happening at this moment? After 25 is added, the reaction no longer increase in temperature. So what does that tell you about the reaction? It's complete, right? The reaction is complete. It means it's done. It means that it has reacted with all of the hydrochloric acid in the conical flask. The reaction is complete. That's part B. See how organized it is? And then the third part is C. How would you explain C? Why would it go down? Why would the temperature go down? Because if the reaction is complete and there's no more reactions to produce the heat, even though you're still adding sodium hydroxide, there is no more release of heat because there's no more reaction. You're just pouring extra sodium hydroxide inside, isn't it? And therefore, after or beyond or more than 25 cm cubed is added, no more heat is produced because there's no more exothermic reaction, no more heat produced, and it just cools down. All right, the solution cools down because there's no more reaction. The solution cools down. It cools down because the room temperature is not as high as the room temperature is definitely not as hot as 32 degrees Celsius. So therefore, it's going to cool down to about room temperature, which is around this. Okay, all right. Okay, question 8. The diagram shows the arrangement of electrons in an atom of calcium and in an atom of chlorine. Here we go. Chlorine here, calcium here. Describe in terms of electrons what happens when calcium reacts with chlorine to form an ionic compound, calcium chloride. This is a typical question on electronic structure and what happens when things react, right? Now I've got these down here for you. So if you have a look, what is this? Calcium and chloride, isn't it? Calcium and chlorine. So calcium is here, which is group 2, and then chlorine is all the way over here, which is group 7. What Why is that important? Because the group number tells you the number of electrons in the outer shell. And the number of electrons in the outer shell tells you how the element will react. So you know that if calcium has 2 electrons in the outer shell because it's in group 2, it's going to lose 2 electrons because then you have an outer shell that's full, right? You have a full outer shell and then you're stable. So how would chlorine react? Tell me. If it's in group 7, it's got 7 electrons in the outer shell. And how do you have a full shell? How many do you need? You need 8. And therefore, chlorine is going to react by gaining how many electrons? Gaining 1 electron to have a full shell, right? Okay? And therefore, how would you answer this? We can already put down what we just wrote down there is that, and you can actually see it here. Take a look. The calcium's got 2 electrons in the outer shell, right? This is the outer shell. And there's only 2. And chlorine's got how many? 7, if you count it over here. So you would say that calcium loses 2 electrons and then to form calcium 2 plus ion. Why 2 plus? Because you've lost 2 negative electrons, right? And then the chlorine gains one electron, yeah, to form the Cl minus, which is chloride ion, to form that, isn't it? So make sure you talk about in terms of electrons, And of course, when you've got a positive calcium and a negative chloride, then the positive and the negative charge will attract each other, isn't it? And therefore, you will have a calcium chloride compound that is formed. Please be careful not to mention anything about covalent bonds here. This is an ionic bond because these are ions, right? And I'm saying that because the mark scheme specifically says any reference to covalent or metallic bonds scores 0 marks. So this is a question on ionic bonds because these are ions. These are ions. Okay, great. And it says, describe tests to show that an aqueous solution of calcium chloride contains calcium ions and chloride ions. So this question is asking you for a test. A test means you must say 2 things. You must tell the examiner what you're going to use to do the test. So what you're going to add or use what? And then what you're going to see. What will you see to confirm that, yes, there is calcium ions or yes, there is chloride ions. So how do you test for calcium ions? This is the flame test. Flame test. So that's what you're using. And what do you see? Flame test means you stick the calcium ion into a flame using a metal wire. Okay, and then what do you see? What color will you see? And I hope you've memorized this. I've put them down here. And a very easy way to help you guys remember is the colors of the rainbow. So there's 5 ions, like metal ions, you have to know that produces a color in the flame. And I just want you to remember this weird sounding thing, which is li, ka, na, cook, right? Li, ka, na, cook. And the reason for that is because it's exactly here. Li, ka, na, cu, and k. Now, the lithium, remember, these are ions. We're testing for metal ions. So it's actually plus, this is 2 plus, plus, this is 2 plus, and this is plus. So these are the ions that you're testing for. And notice how I've arranged them in the colors of the rainbow. So if you know your colors of the rainbow, it becomes easy to remember the flame test, because I know the flame colors are not always straightforward to memorize. There's no blue color, by the way, but everything else follows the color of the rainbow. And I just realized this rainbow should not be having that pink color, because there's no pink color in the rainbow, so that's not the most accurate rainbow. I'll correct that later. But the main thing is li, ka, na, cook, and these are the colors from the flame test. And therefore, what is the color of calcium ion? Orange. See? So once you memorize this li, ka, na, cook, then it becomes easy to deduce the color of the flame test. So therefore, I'm going to see an orange flame. Orange, or sometimes they call it orange-red flame. Okay? It's orange-red flame. Okay. And just a bit of a word about a flame test, because sometimes they could ask you about that. So how do you do a flame test? That's usually like a 3-mark question. You use a platinum wire, sometimes nichrome, and the reason for that is because it is inert and it has no flame color, because you don't want the platinum wire to have a flame color, because that would be very confusing, isn't it? And also it's inert means it's unreactive, and also it has a high melting point. So that's 3 reasons why you would be using a platinum wire. That's sometimes also asked in exam papers. So I'm gonna use a platinum wire. You don't want it to melt, that's why it's got a high melting point. Platinum wire, and then you dip it in hydrochloric acid to clean it and get rid of any impurities, and then you dip it in the metal ion, and then you put and then you dip into your metal ion, and then you're going to put in a roaring flame. Roaring is like the really hot part of the flame. Sometimes this is also called non-luminous flame. I've seen that underlined in past papers, which means that it's a key word you have to put down. Non-luminous means, again, it's the very hot part of the flame, because if it's luminous, means it's see-through. Think about it. When a flame is see-through, it's a pretty weak flame, and it's not hot enough to produce the color change. So it's important to remember how a flame test is done, what you're using, the platinum wire, and what is the Bunsen burner like. You're using a non-luminous flame. Okay, so that's everything about the flame test. Moving on to chloride ions. How do you test for chloride ions? Look, there's 4 marks. So 1 mark for what you're using and what you're seeing. Same thing for the chloride. What are you using and what you're seeing? So how do you test for chloride ions? What do I use? Over here is the chloride test. So for chloride test, what you need to add, what you're adding is silver nitrate, and nitric acid, HNO3. Sometimes you see that written as acidified silver nitrate. This is silver, Ag is silver. So acidified means there's acid, and that's this acid here, the nitric acid. Silver nitrate, which is this one. And why are you adding that? Because when you have a solution that is either chloride or bromide or iodide, these are the halide ions, what happens is this silver, which has a charge of +1, is going to combine with this. And when you combine it, you're going to get AgCl, silver chloride. Similarly, it will combine, the silver will combine with the bromide, because positive and negative, right? You get silver bromide. And then this one would be silver iodide. And the color is white for silver chloride, cream for silver bromide, and yellow for silver iodide. And just please add 1 word after that, which is precipitate. Means that it is a insoluble substance in there. It's insoluble. So you're going to see either white, cream, yellow, depending on if it's chloride, bromide, or iodide. Understand this? And therefore, coming back up to this question now, when it's asking for chloride ions test, you're going to add silver nitrate and also nitric acid, and then you're gonna see a white precipitate. White because it's chloride. If it's bromide, you would put cream, and if it's iodide, you would put yellow. Okay, part C. Solid calcium chloride does not conduct electricity. Aqueous solutions of calcium chloride do conduct electricity. And that's an important point I hope you know, because why doesn't it conduct when it's solid? Because the calcium chloride ions are not mobile, because it's a solid. They're fixed in place and they're vibrating on the spot, so they cannot carry a current. That's why it does not conduct electricity. But if you dissolve it in water, so it's now aqueous, it can now swim around. The calcium 2+, and the chloride 1- can now swim around and therefore conduct electricity. Okay, so it says a student uses this method to investigate how the conductivity of a solution changes when the calcium chloride is dissolved in pure water. And what he does is he adds 100 cm cubed of pure water to a beaker, and then he adds a spatula of solid calcium chloride to the beaker, and then he stirs it, which will dissolve it, and then he measures the conductivity, and then he repeats it until 9 spatulas of calcium chloride have been added. Right, so he adds more and more, and then looks at how the conductivity changes as you have more added. All right, so let's look at here. It says plot the results on the grid and draw 2 straight lines of best fit. So I've already plotted it for you. This is the data from the table above. And then it says ignore the anomalous result. Who's the anomalous result? Can you spot it? Can you spot it? Which one's not following the trend? Is this one, isn't it? And then in an exam, you can even circle it. You can circle an anomaly just to show the examiner that you've noticed that. And how would you draw the lines of best fit? It says draw 2 straight lines. Read it carefully. It's not curve, it's 2 straight lines. And you would draw it, like this, ignoring the green one, right? Ignoring the anomaly. Make sure it goes through the dots, the plots, and then a straight line through that. Like that. Be very accurate. Ooh, it's a little off. Okay, that's a little. Okay, yeah. So you would draw the line of best fit like that. And part 2, it says state the trend shown on the graph for the first 6 spatulas. So up to here, right? What's the trend? What is the trend? How would you describe what this graph looks like? It's a positive trend, first of all. When you describe graphs, always talk about what happens to y as you increase x, right? So as I increase x, what happens to y? Y also increases. So just literally write that down. So as number of spatulas of calcium chloride increases, right? The conductivity also increases. This is also called a proportional, or even you can say a directly proportional relationship. Directly is because it's a straight line. Directly proportional relationship. Directly proportional. Okay. Part 3, suggest an error the student could have made to cause the anomalous result. So whenever you try to explain anomalous results, you have to understand what's going on. At 3 spatulas, where would you expect the plot to be? You would expect it to be somewhere around here, isn't it? You would expect it to be there, but it's actually lower. It's the green one here. It's lower. What does that mean? It means that you're supposed to have a higher conductivity than what you actually got. So how could he have gotten a lower conductivity? What could be a cause for that? One reason is that maybe he didn't stir it properly, because when you add another spatula, when you add the third one in, right, if you don't stir it properly, the calcium chloride will not dissolve properly. And if it does not dissolve properly, it's not going to be able to do the conduction as much, right? So did not stir the mixture properly. Did not stir the mixture properly. Another reason, if you really observe it, is that, do you see how for 2 and 3 spatula is actually exactly the same spot? What does that tell you? It tells you that nothing really happened between 2 and 3. So maybe he did not even add the spatula, or he wrote down the reading before he added the spatula, right? So that's one reason. Another reason is recorded conductivity before adding the third spatula. Okay, question D. Describe another way to make solid calcium chloride conduct electricity. How else can you remember what we said? If the calcium chloride is a solid, it would be regularly arranged and not moving, just vibrating on the spot. So how can you turn that into something that is now liquid or able to move? You could either, one way is to dissolve in water. But that's what he did already, isn't it? That's what he actually did. So what's the other way they could make them move? How else can you do it? How can you make it into a liquid? You would literally just melt it. We call it molten, melt or molten. So actually the answer is 2. You would melt it because 1 is already done. He's already done that. That's why he's asking for another way. And notice it's 2 marks, right? So if your first mark is saying, I'm going to melt it. Oops, let's just worry about the first one. I'm going to melt it. What's the second mark? How are you going to melt it? How do you melt it? You add heat, right? By heating. So orange box is on ionic compounds, in this case calcium chloride. Remember, ionic compounds, when they are either molten or aqueous, which means that it's dissolved in water, the ions are free to move, and therefore it can carry a current, and that's why it's able to have a conductivity. It's able to conduct electricity. When ionic compounds are solid, they cannot conduct electricity because the ions are not mobile. Also, in terms of plotting graphs, make sure every single one of your plots are accurate. They do check every plot within half a small square accuracy. And when you draw the line of best fit, make sure you ignore the anomaly. Purple box was on enthalpy change and exothermic reactions in this case. Remember, exothermic reactions release heat, and that's why the temperature goes up as you add more sodium hydroxide. Also, notice how we explain and describe graphs. When you look at a graph, look at the overall trend first. It's going up, it's going down. So that's what you're going to discuss, going up and going down, and the reasons for that. And also, the turning point is clearly an important thing to discuss, which is at 25 cm cubed. That's when the temperature starts to drop. Blue box was on acids and bases. Remember, acids have a low pH, and the color would be red and orange, whereas bases or alkalis have a high pH, and the colors will be blue or purple. And when acids and bases react, they will form water, and this is called a neutralization reaction. Water is neutral, pH of 7, green color. Also, make sure you know the different indicators over here and their colors in acid and base. Pink box was on the flame test. Remember how to do a flame test. Use this platinum wire, which is inert, means it does not react. It has a high melting point, so it does not melt, and it doesn't have any flame color itself, so it doesn't confuse you. And then you dip that into the metal that you're testing, and then you put it into this Bunsen flame. The Bunsen flame has to be non-luminous, sometimes called roaring, in order to be hot enough to see the color of the flame. The actual colors of the flame is in the order of the rainbow. Then finally, green box was on the test for halide ions. Halide ions is the ion of the halogens, the chloride, bromide, and iodide ions. How do you test for them? You need to add acidified silver nitrate. The acid would be nitric acid. You're going to add nitric acid with silver nitrate. And if the solution had chloride ions, you're going to see a white precipitate. If it had bromide ions, you're going to see a cream precipitate. And if you have iodide ions, you're going to see a yellow precipitate.